Hi, everyone. This is Dr. David Branham. Welcome back. This is Chapter 7, Part 2 video for Chapter 7. As you know, in Chapter 7, Part 1, we went over experimental design, quasi-experimental design, and so forth, factorial designs, ways that we model these designs so that we can do hypothesis tests with them. This video, Part 2 of Chapter 7, will look at the actual calculation. How do we determine, after we gather the information from these models and do the test, how do we determine if those results are statistically significant or not? So I'll start by sharing my screen and to where we left off in Chapter 7. Okay. And we left off with inferential statistics, statistically testing hypotheses in quantitative research designs. So this was the second part of Chapter 7. It'll be a little shorter than the first part. But now that we've covered several inferential research design, we can now cover the statistical procedures used in testing the hypotheses presented in these models. Now, understand that this is going to be a procedural coverage, not a calculation exercise. You're not going to be doing calculations in as far as statistical calculations. Even in statistics class, I pretty much avoid you doing the calculation itself, because computers do them so easily now. I'm much more interested in you being able to comprehend what you do with these calculations and what they mean. So this will not be a calculation exercise, and it will not be a comprehensive review. We're not going to spend a whole lot of time on it. Instead, its purpose is just to introduce you to the procedures, and they'll be covered in depth in SOS 3312. But in this introduction, you can have something of an understanding of what is done, so that when you write your paper, you'll have more ability to write it in a comprehensive and intelligent manner. So we have two types of hypotheses: the alternative hypothesis and the null hypothesis. Now, we can reject hypotheses based on contrary evidence, but can never truly accept hypotheses, because the presence of evidence doesn't mean that we may not observe contrary evidence later. So we never can accept hypotheses. We can say the evidence provides support for the hypothesis, and so forth. Statistics never proves anything. People hear that and say, okay, statistics never proves anything, so why do we bother? Why do we bother is because it gives us a lot of evidence. It helps us understand the world better, because we can see things more clearly, but it doesn't prove anything. Like, for instance, I can't prove that the sun will come up tomorrow, but I can show you that the evidence says that it will. So we don't accept the hypothesis, but we can reject hypothesis based on contrary evidence. Because we cannot truly accept a hypothesis of interest, the alternative hypothesis, we formulate a null hypothesis as the opposite of the alternative hypothesis. That's what we do in statistics. We formulate the null hypothesis. It's opposite of the alternative hypothesis. We're going to state our alternative hypothesis, but then we're going to use empirical evidence to reject the null hypothesis to demonstrate indirect probabilistic support of our alternative hypothesis. So understand, we can't accept a hypothesis, but we can say the evidence rejects this. And so our goal, when we have a theory that turns into a hypothesis that we're going to test, our goal is to reject the null hypothesis that there is no effect, and say that the evidence supports the alternative hypothesis that there is an effect. A statistical is how we know whether or not a relationship between two variables is in an observed sample is significant. It's not a matter of chance. We have over time in the social sciences, we have said that a statistical result may be considered significant, and can be if it can be shown that the probability of it being rejected due to chance is 5% or less. So if our data says, okay, we have this difference, and the chances of this difference just be by chance is less than 5%, then we can say we're going to reject the null hypothesis. And we're going to say that the alternative hypothesis, the evidence is supporting the alternative hypothesis. And in inferential statistics, this probability is called the p-value, where 5% is called the significance level. The p-value is less than 0.05 or 5%. It means that we have a 5% chance of being incorrect and in rejecting the null hypothesis. And if we are incorrect, then we have what's called a type 1 error. So a type 1 error occurs if, as we said, there's less than a 5% chance that this is by chance, but there's really no, let me start over on that. If we say if we say the null hypothesis is there's no effect, and then we say the evidence shows that there's less than a 5% chance that no effect is true, we're going to reject that null hypothesis. Sometimes it does fall in that 5%, even though by chance, the chances are very slim. There is a 5% chance that we'll have that type 1 error, where we say, okay, we can reject the null hypothesis. And the reality is the null hypothesis is actually true. That's called type 1 error. Now, we don't have a lot of type 1 error because it only happens 1 in 20 times. Because it's less than 5% chance. Because 0.05 is such a high standard, there are times when 0.10 is actually accepted as a p-value in social sciences. Most of the time that occurs when the sample size is low, less than 1,000. If you have a small sample, it's harder to get statistical significance. So sometimes you just say, okay, I'm going to make it at 0.1 if the journal allows you to do that, and lots of journals allow you to do that. We don't want to throw the baby out with the bathwater. If we show at the 0.10 level that we can reject the null hypothesis, then all of a sudden, then our type 1 error percentage goes up to 10%. But that means 90% chance that we're correct, that the null hypothesis is incorrect, and the alternative hypothesis, the evidence supports that. Okay, the general linear model. The general linear model is a model of estimation of a mathematical equation that can be used to represent a set of data. And linear refers to a straight line. So if we have linear data, we assume that in a general linear model, we assume that relationships are linear in nature. Now, we know that all relationships are not linear in nature, and we do have ways of manipulating the variables to capture that. But in the general linear model, where we start, we do assume the linearity. So a general linear model is a system of equations that can be used to present linear patterns of relationships in observed data. This is what we do in experimental design. And this is what we do in further tests beyond experimental designs, such as regression and so forth. So the simplest type of general linear model is the two-variable linear model that examines the relationship between one independent variable, the cause or the predictor, and one dependent variable, which would be the effect of the outcome. And the book has an example here of a bivariate scatter plot that presents a general linear model. Now, if you remember back to high school algebra, we remember that equation for a line. Remember, y equals mx plus b is the equation for the line. That's what the general linear model does. It has an equation for the line, and it's a linear equation. So here in the one variable model, y equals BO, which means BO is just a constant. The BO is where the slope hits that y-axis. So you can look on this little chart here, and you can see that BO is actually at 2.0. That's where the slope touches the y-axis. So it's the constant, or called the intercept, where it crosses the y-axis. So that means in a one variable model, if the independent variable equals 0, then y equals the constant. That's the prediction. So on this one, which has a y-axis for self-esteem, it has the x-axis for age. When your age is 0, your self-esteem measure will be 2.0, because that's where the y-axis is when age is 0. So in that model, if your age is 0, then y would equal 2 plus 0, which means that your self-esteem at age 0 would be 2. As you can see, as you get older, the model predicts more and more self-esteem for a person as they get older. By the time they get 50 years old, that self-esteem measure is nearly at 5 on this model, on this linear model. But you do notice on this bivariate scatter plot with one independent variable that there's a lot of error in there. You can see those blue diamonds. What that line does is it goes through at a general least squares in a model where what it does is it makes the least possible squares added up so that you can have the least error. So what that line does is it goes through those dots at the closest point it can to each dot. And it's got to be a straight line. So in some cases, the dots or those diamonds, those blue diamonds, are off. The reason those blue diamonds are off are, 1, it could be measurement error, or 2, it could be just some other variable impacting your self-esteem, which there are many of them. So self-esteem goes up as you get older, but for some people, it's much higher. Perhaps they have a college degree. It could be education that impacts your self-esteem. That would require us to put another variable in the model. In this case, we haven't done that. We're just looking at one variable to see its effect. And we can see that B1, the variable B1 is your age. That is the variable. As that age goes up, then self-esteem goes up in a linear fashion, with E being the error. It's an error term, which says if that blue diamond's off the line, however far it's off the line, that's the error. So that's the general linear model that's used in most statistical analysis for these experimental designs, and when we go up to linear regression and so forth. So we're looking here at a 2-variable model, and it's very simple. So it's the simplest type is the GLM model. You could actually calculate these by hand. I've calculated these by hand before. You can calculate these by hand quite easily. And so it's something that's very, very pleasing. But I mean, in this case, it looks like there's a linear relationship. And it looks like the things affect that linear relationship more as you get older. You can see the error term tends to get a little further away from the line for the 30 and 40-year-olds than it does for the 20-year-olds. Things happen between 20 and 30 that cause that line to go up. So that's the general linear model. So I put a regression, a general linear model equation here for 3 variables up here in the orange. Y equals BO plus B1 X1 plus B2 X2 plus B3 X3, and then I have dots. And the reason why I have dots is because you can actually add as many variables as you want to this regression equation. It is linear. So we're assuming that all relationships in this are linear, which is a tough assumption. But remember also at the end is that error term. We know that in most cases, error is not 0. So you put that error term in there to calculate the error. And anytime there's error, you got one of 2 things, either a miscalculation or something's being left out of the model that can make your prediction even better. So on this variable, we have covariates or additional independent variables that can be added to that linear model that we had before of self-esteem and age. So we can add these covariates to the linear model. We can have age as 1, we can have education as another, we can have gender as 1, and we can see if those actually have an impact on the dependent variable. Maybe they're 0, maybe they have no impact at all. But we can put that data in to see what that impact is. In this equation, y would be why would be self-esteem? That self-esteem measure that we have. Remember, when you were age 0, it was 2, and then it slowly climbed up to 5, and then more as you got older. So why is the self-esteem measure? BO is the constant, or where that linear line crosses the x-axis. In this case, it's where what your self-esteem is at birth. That is the BO. That's the constant. So if all these other variables are 0, then the constant. So you have 0 age, 0 education, 0 annual salary. If all these are zeros, that means you're just born. And so your self-esteem is going to be at that 2.0 level. So in this model, B1 is age, B2 is education, B3 you put in is salary, but you could add others like gender. You can do whatever. You can add any variables that you have the data on to see what the impact is. And a lot of if the impact is 0, if a independent variable has no impact on dependent variable, which would be self-esteem, then it should be 0 in your model. For instance, if you put gender in there and gender has no impact on self-esteem, then it should be 0 coefficient in that model. So B1 here equals age. X1 is that coefficient for age that the model says, okay, for each year that you add on, this is how much self-esteem score you should add. You can see that the self-esteem score is at 2.0 and climbs at it up to 5.0. So each year is probably adding less than 1/10 of a point to that self-esteem score in that model, or it's right at it. So that's what that X1 is. It's a coefficient. What do you multiply it by? So if age is there, B1, the coefficient for that should be about 0.1. So you would take your age and multiply it times 0.1, and that would tell you how much you add self-esteem to your self-esteem score as a prediction of your self-esteem. So B2 equals education, B3 equals annual salary, BN equals the more variables that you have, and then E equals the error. This is your general linear model equation. And it's a way that we make a prediction of the dependent variable from a several or a line of independent variables that we can have to test. The GML specification, the most important problem in general linear model specification is how to specify a regression equation to the best interest of the phenomenon of interest. So how do we specify self-esteem? If I were to go back, I'm going to go back real quick to this model here. And we see we have a lot of error. And that means there's something going on that we're not measuring. Now we're measuring it incorrectly. The hardest part about these models is modeling the independent variables that actually have an impact on the dependent variable. For instance, you may have a problem with something that correlates with age that also affects self-esteem. And it could be that it's not your age that affects self-esteem, it's something else going on. Could be your education, because education pretty correlated with age, especially up to 25 or so. So it may be the education. Once you put education in the model, that age may actually go away and become 0. So the hardest thing about these models is specifying where you get all the variables that truly have an impact in your model, so that you can control for possible instances where you have correlates or correlation where it really isn't causation and it's really just some other variable going on. So for instance, if this model cut off at 25 and you put education in, it could be that age really doesn't matter anymore. And it's just really education that's driving self-esteem, or it could be something else. So the hardest thing about the general linear model is specification. The role of data is in validating the model and not in its specification. So the model specification should be based on theoretical considerations. So you shouldn't just pull things out of the air and throw them into a model and see if they stick. So everything that you put in should be theoretically, I say theoretically pleasing, in that, for instance, it's theoretically pleasing to put education in as something that determines self-esteem. That makes sense. The more education you have, it would make sense that you would have more self-esteem, be more proud of yourself. So that's theoretically pleasing. If you want to put in the model something that doesn't make any sense, that you think may be correlated with it, or you find some correlation to, something that would cause self-esteem. If you were to say something like, which way your house faces, okay? If your house faces to the north, then you have more self-esteem. That's not really theoretically pleasing. I mean, that doesn't really make sense. You may find that correlation there, and you might put it in the model, but it shouldn't be in the model, because theoretically you can't make sense of the way your house faces helps your self-esteem. Now, there may be something else going on that causes the correlation to occur. For instance, you may live in a neighborhood where you have lake houses that all face north, and that means you have a higher income. That may make sense, but the facing of the north is not the cause. It's your income that's the cause. So you need to put the income in the model, and not just put in these what a friend of mine calls garbage can models. You don't want these garbage can models. You want specification to come from theoretically pleasing reasons to put variables into a model. Two-group comparison. One of the simplest inferential analyses is comparing the post-test outcomes of a treatment and control subjects in a randomized post-test only control group design. I talked about this in part 1, that this was the simplest design. And the example is, whether the voters, in this example, whether voters went to the polls more often when they received a solicitation to vote. You're going to see this again. So this is something I would pay attention to. So this example, do voters go to the polls more often if they get a card saying to go vote for this person? So in this case, the predictor variable is a dummy variable. And what I call dummy variables are categorical variables, or they only have 2 values. 0 in this case, no, they didn't go to vote, and 1, they did go to vote. So you have a treatment group that gets the card. You have a control group that does not get the card. And you have random assignment. So what you do is you give the card to the treatment group, you give nothing to the control group, and then you sit back and wait and see if they voted. So the null hypothesis would be that the solicitation doesn't matter and whether or not people will vote. Null hypothesis is you can give them the card if you want. It doesn't matter. It won't change whether or not they go vote. There's other things that may cause it, but not that card. So you have that. The alternative hypothesis is people who get that card are more likely to go vote. You remind them to go vote, they're going to go. So what you do is you give them the card to the treatment group. You don't give the card to control group. Then you go and find out if they voted or not. And then you do a statistical test to see if the turnout of the control group was lower than the turnout of the treatment group, which is your alternative hypothesis, because you think people are more likely to go. So conceptualizing how these t-tests works. In order to run it, to see if there's a difference, you run something called the t-test. They call it a student's t-test in the book. Almost everybody just calls it a t-test. And it should be understood that the t-test only tests to see if there's an actual difference between the dependent variables. It doesn't look for size effect. All it's looking to see is, can we reject that null hypothesis? Because that's the hypothesis we're testing. We're not testing an alternative hypothesis. We're just saying we don't think that null hypothesis is true. We're trying to show that there's a 5% chance or less that it actually is true. Because if there's 5% or less chance that it's true, our alternative hypothesis is supported. So that's what the t-test does. If you get a really big t-test score, you can't say, well, the size of the effect is really large, because you're not testing for effect size. The t-test looks at 3 things to see if the null hypothesis can be rejected. It looks, 1, at the differences between the 2 sample means. If the mean differences in the dependent variables are larger, then you got a better chance that you're going to find significance in the t-score. So If you have a large difference in means, that's better than a small difference in means, because the effect, the initial effect that we see with the means is smaller. So that makes just the most intuitive sense. If if you're testing height and you say this group is taller than this group, and there's an 8-inch difference between the two groups, that's pretty big. And this, if you got a 2-inch difference, that's not nearly as big. So you got a lot better chance of getting significance with the 8-inch difference than the 2-inch difference. Doesn't mean the 2-inch difference isn't going to be significant. It just means you have a better chance with the 8-inch difference. The second thing is the sample size. And I talked about this a little earlier, but the sample size, the larger it is, I talked about it in part 1, the larger the sample size is, the more likely there's going to be different. If there is a difference, that you'll find significance. You got to have that difference first. If you don't have that difference of means, then you just go ahead and throw it out. The test is over. If you're saying that people get that solicitation are going to go to the poll more often, and then you find out that the means of them going to the polls was the same, the solicitation did nothing. So you just throw it out and say, okay, this test is over. You got to start with people going to the poll more often if they got the solicitation. If you don't have that, then you don't have a test. But then once you have that, you can find out, is this difference significant? If it's a little bit, then it helps to have a big sample size. If you have 100,000 people and the turnout is 45%, and then you have 100,000 people who didn't get it and the turnout is 43%, that's going to be significant because you have so many people in your sample. The difference isn't big, it's only 2 percentage points. But the sample is so big that it'll be impossible for us to say that there's not a significant difference. So sample size matters. The bigger your sample size, the better chance of finding a difference if there really is one. The last thing it looks at is the variance of the dependent variable within the group. Now, the variance isn't going to be big in a sample when the dependent variable is 0 and 1. But it can be there. But the thing is, if you got a card and the variance, is if more people, let's use a different example. Let's use an example with a continuous dependent variable, like the age of somebody who goes to see a movie. Okay, you can have a movie, and you can hypothesize that people who are older will go to this movie number 2, then they go to movie number 1. So you take the average age of movie number 1, and it's 47. And then you take the average age of movie number 2, and it's 49. And I said, wow, that's not a big difference in means. What will determine whether or not that's different? One is how close people are to the average of 47 in the 47 group. If everybody in group 1 is 46, 47, and 48, that's a very tight variance. And you're much more likely to find statistical significance. But that would be rare. If the average is 47 for a movie, in almost every case, you got a spread of everything from 8 to 80 in that movie. And then if you have an average of 49 and you still have the big spread of 8 to 80, you got so much overlap in your groups that you're probably not going to find significance in that situation. You need that variance to be narrow. So where it can often happen is if you look at movies for young kids. For instance, you might have a movie for 3-year-olds and a movie for 6-year-olds. And you find the movie for 6-year-olds has an average age of 6. The movie for 3-year-olds has an average age of 3. And is there a statistical difference? There's probably a big statistical difference because very few 6-year-olds are going to go to the 3-year-old movie and vice versa. You're going to have very tight variance in the age group of group 1, 3, 4, and 5-year-olds, or 2, 3, and 4-year-olds. That's it. That's who's going. And the other group is going to be 5, 6, 7, and 8-year-olds. That's it. So those are tight variance groups. In that situation, you're much more likely to find statistical significance and say that, there's less than a 5% chance that those groups are equal because of the tight variance inside the groups. So those are the 3 things the t-test looks at when it determines whether or not something is statistically significant. So After that, you have your research procedure. To conduct your t-test, you must, one, compute a t-statistic of the difference of the sample means between the two groups. The t-statistic will be positive if the treatment mean is greater than the control mean. So first, look and see, is that treatment mean greater than control mean? Do people vote more if they get the card than if they don't? If they don't, test is over, it's done. But if they do vote more, then you have to find out if that difference is significant. So to examine if this t-test is significant, it's large enough. If it's large enough, then by chance, then we would look up the probability of the p-value associated with our computed t-test in the statistical table. So you actually go to a statistical table and look, this is my t-score. Is this significant? And usually what you find is, if you have a big sample sizes, it's 1.96 for two-tail test, 1.65 for one-tail test. If your t-test is over 1.65, then it's significant if it's a one-tail test. In this case, one-tail test, it was over it might be over 1.65, it's significant. So you don't need a really big t-score, but if you have a t-score of 10, you can say, okay, it's statistically significant, or t-score is 10. But you can't say the effect size is really big because it's 10, because the t-test doesn't test that. It just tests to see if there's a difference. Now, if it's less than 1.65, say it's 0.4. You still have means that say there's a difference, but that difference isn't going to be statistically significant at the 0.05 level because your t-score is too low. Now, it doesn't mean you reject the alternative hypothesis, because your evidence actually says the alternative hypothesis is true. Your means show that people are more likely to go to vote. But we can't say with that 5% type 1 error possibility, with that as our criteria, we cannot say that that's significant because our criteria is 0.05 level. So that's what you do in the t-test procedure. We will do this more in stats. If you take SOS 3312, which I teach as well, we'll do this in more detail. But you need this for your paper, because in the paper, your results section are going to display t-score results. So you'll need to know about that, and you'll need to know it for the test as well. Quantitative analysis tools in addition to the t-test. Ordinary least squares regression, that's a tool that we would use for doing those GLM linear models, those generalized linear models. Remember when I had that long equation there? Ordinary least squares regression allows you to put in all these variables, put in your dependent variable, and see if those variables are significant. It gives you a t-score for every single variable, and it gives you a prediction on how strong that variable is. So on this one, it will give you a strong prediction for age, being a predictor of self-esteem, because you have that nice long slope, that nice angle slope. If in this model, if age didn't matter in self-esteem, the line would be flat. It wouldn't be slope. That slope says there is a positive effect. So you will get that coefficient, and you'll get a t-score in the OLS regression. So ordinary least squares regression is something you'll almost certainly run into if you do any more statistical analysis later on down the line. In stats class, if you take my stats class, we'll cover it some. If you go to graduate school with any kind of quantitative training, you will cover it there. It will be something that's very much a part of your statistical training, and it's going to be very helpful to you in the workforce. If you have a question on it later on when you get in the workforce, you all of a sudden, oh, I remember Dr. Brown talked about OLS regression. I don't remember anything about it. Shoot me an email. I want you to look good after you leave UHD. So I'm always here. And I'll help you interpret what you need to interpret, or design what you need to design. I mean, you just keep my phone number, keep my email address. If I'm able, I will help you. These are great for general linear models. They use that same equation line that we use, that y equals mx plus b equation line. with all those variables. It assumes linearity. It assumes a continuous dependent variable. So we can't use that 1, 0 for that I use for voting as an example. You can't use that in OLS regression, but you can use it in probit regression, which we're going to cover in a second, which is just an offshoot to help you when you have that. OLS regression allows for multiple independent variables in your model. That's a big tool because it helps you control for outside forces. Sometimes your model is just covariates, just to make sure. If your hypothesis is that age helps self-esteem, you're going to need to put that covariate of education in your model just to show people, even controlling for education, age matters. You'll need that in your model. And it produces, like I said, it produces t-scores for all independent variables. OLS regression is a great tool. So when you get to it in stats, pay attention, do well on it. And I'm happy to answer any questions you have on it. Probit regression allows for non-continuous outcome of a variable that's categorical. For instance, the variable that I'm talking about on the paper in the previous slides was whether or not you went to vote. So you would code that 1 if yes, you went to vote, 0, no, you didn't go to vote. That's only 2 values. OLS regression assumes that you'll have a continuous dependent variable, not just 2 values. But probit regression allows you to have that variable with 2 values. And it does pretty much the same thing as ordinary least squares regression. It allows for lots of independent variables in the model, and it produces a t-score for all the independent variables. Logistic regression does this almost the same thing. So if you run into logit or probit, you understand it's for those 1, 0 categorical variables. In the paper that you're going to do, the results are going to show a probit regression because the dependent variable in that paper will be 0, did not go vote, 1, did go vote. So that's our quantitative analysis tools that you should remember for the test and for your paper. Big thank you to all of you. I hope everyone had a great day and has a great day going forward. And let me remind you that if you have any questions, let me know. This will end part 2 of chapter 7, and we'll end chapter 7 as far as videos go. I hope everybody has a great day. Thank you very much.